So hello everyone, and welcome to your CSE 564 Visualization Visual Analytics. This is the introduction lecture, the first lecture I'm going to hold. So I want to start off with asking a question. Why are you here? Why did you attend? Why did you sign up for this class and looking forward to take it? Maybe it's because of this curve here that you're going to see in a second. This curve here. Actually, this is the first visualization you see, this little innocent plot here. And what it is, it's the growth of jobs mentioning data visualization as a skill from 2010 to 2017. You can see this has steadily increased from only 2018 jobs in the beginning on the left-hand side, and then it all went up to 30,000 jobs in 2017, a 16-fold growth. Okay, so this shows you like they're doing the right class. And I want to go a little closer to this, tell you about the top job titles that list data visualization as a skill. So the first 34% of these jobs are data analyst job. Then there's the next is business analyst, software development engineer, 10% business intelligence analyst, then business intelligence developer, data architect, software developer, and so on. So you can see data analyst, of course, they all need data visualization and data analysis. Data analyst is a hot job, but also business analysts and software development engineers and business intelligence analysts, they all need visualization. Okay. So when you look at the other skills that are also listed in these jobs that require visualization or ask for visualization expertise, 15,000 of these 30,000 jobs have communication skills listed, that you need to have good communication skills. 11,000 of these, one third of them, have research, Microsoft Excel expertise, problem solving, creativity, writing, should be detail oriented, should be able to plan things, presentation skills. But what's really striking is with communication skills. Okay, there's actually half of those jobs is also required to have good communication skills. So why is this? Because when you look at communication, what really this means in this context of visualization, it really means that you're supposed to communicate information derived from data, but you're supposed to do that visually. Okay, you're supposed to do visual storytelling with data. Okay, turns out actually a study by Cart and collaborators in a Gartner report 2013 showed that half of the data analytics projects they had failed because they had poor communication. This could be communication of the hypothesis, this could be communication of what came out of the project, or how to plan the project, or to communicate the results. Communication is the very, very important skill, and people more and more figure out that visualization is a good way to communicate. Okay, so this is why this class is very worthwhile to take. So there are other skills that were mentioned in these jobs that mention visualization as one skill. These are more general skills. Okay, or proficiencies. Commonly listed was SQL. Another one was Tableau, which is a visualization software, sort of a package. Then Excel and PowerPoint. Python, one third was Python. SAS, R. You can see R is actually only half of Python. Plotly is another visualization library that we're going to talk about. I don't have any data how much was listed. And then one thing that's very important is JavaScript and JavaScript-based data-driven documents, which is a library or API, D3.js, 13%. So we're going to be focusing in this class on D3.js and visual storytelling with data. Okay, we chose this D3.js because it gives you much more freedom in designing visualizations, designing dashboards than Tableau will do. We'll talk about Tableau, we'll also talk about Plotly, but we're going to focus on data-driven document because they enable you to create applications in a web browser that run in a web browser powered by JavaScript and HTML. And you can pretty much design anything there. You can create new applications completely out of the box. Tableau is more of an environment. You can you call up Tableau, you put your data in, you create a visualization based on that. And lots of people use Tableau, and we're going to talk about it too. But I want to really stress for developers and computer scientists should learn D3.js. It's a very popular package. Okay, so let's move on. Visualization is not new, of course. Visualization has been around for a long time. And I want to give you like one specific visualization use of application that came in really handy, and it saved a lot of lives 160 years ago, or more than 160 years ago, in London, England, 1854. Which looked like this. Back then in 1854, London, England, there was no cameras, so people had to draw it. That's how it looked. There was you can see there's a lot of misery going on. It's very crowded, but a lot of misery. And actually, this was the year there was a very deep cholera outbreak, okay, in London, around a specific area in London, Broad Street, Golden Square, Cambridge Street. Around that area, there was a cholera outbreak. And just within a small area, there were like 500 fatal attacks of cholera within 10 days. It was very serious, okay. And you may have heard of it, movies were made out of it too. And it was actually the biggest plague ever, the biggest outbreak of anything ever, even bigger than the plague. And that was already very famous, right? And much more sudden. There was like in just a short amount of time, lots of people died very quickly. So something had to be done very rapidly. So people were asking, what can we do? What is the cause? And how can we eliminate it, right? So it's a big serious issue, right? You could be next. So there was this doctor, John Snow, has nothing to do with the TV series. So he had this imaginative idea of taking the data, putting it on the map, using a map or draw a map of this critical area, Cambridge and Broad Street, and each dot here is basically a dead person. Okay, each dot is a dead person. And he said, okay, let's plot that and see, okay, interesting, there's a cluster around. There's a few outliers here, but most of them are sort of contained in this area here. And let's see, let's also look at the wells, interesting. There's a cross here. That is actually a water well. Back then, you couldn't just get water out of the faucet. Back then, you had to walk to a well with a bucket and fill it up and take the water home. Right? So there were all these dead people around this particular water well here. There was also a dead person around this water well here. So it's kind of interesting, but it's an outlier, okay? It's another one here. And so he said, okay, that's interesting, okay? So mark that, look around. And then he had this hypothesis. And then actually that was a hypothesis, already a long-standing hypothesis, that cholera spreads through water. That wasn't a new hypothesis, that was actually something already existed, but no one could prove it. Okay, and then there was always this antagonist that said, no, cholera spreads, that's like, comes from the old plague victims, they caused this cholera from the burying grounds, and then, they cause disease all around. We should have buried them better. It's like almost like a curse, and other fantastic causes, but no one could ever prove that. So now basically the bacteria was discovered much later than this cholera incidence, 1886. So this whole outbreak, cholera outbreak, actually was a real life experiment, which is often the case with observational data, right? You come across some data somewhere and you can use it to conduct an experiment based on those data and then can prove the hypothesis or not, right? Or disprove it. In this case, there was a real life experiment, lots of dead people by some cholera disease, not knowing where it came from. Now, you look at the map and you can see, there's a water well right in the middle. It's an easy guess. Must be the water that's contaminating all these people. So let's shut it off. Go and shut it off. And then what happened? After shutting it off, the cholera subsided, right? It actually went away. Cholera outbreak was solved. Okay, that they had to do something about the water that came out as well. But, at least no one was drinking from it anymore. Okay. So what this did really much, what the visualization provided inspiration to actually try to address this hypothesis and prove it by turning the water off. And it also gave convincing arguments to justify this, because officials need to be convinced to cut off the water, right? I mean, they wouldn't cut it off otherwise, right? They have to be convinced, let's cut it off because it could maybe solving the cholera problem. And visualization actually had two measures here. It helped figure out what was the cause, and it also helped to create the action to fight it, and also convince people in charge to actually take that action. Okay, so this John Snow is a very historic figure nowadays, and there's actually a bar around this Broad Street pump, and you can safely drink your Guinness there. And so so basically this is a really good example for visualization. So what is needed for visualization then? So we learned a very early case of it. What is needed? So the first thing you need is data, right? So the first thing to create a visualization, you need something to visualize, which is data. Then you need an algorithm. Something that creates the visualization is something that analyzes the data underneath, so algorithms. Then you need a computer to run those algorithms. You need storage. And you need humans, right? Without humans, you can't, there's nothing, who's going to consume the visualizations, right? So, the humans are the customers, the humans are the consumers of your visualization. If you don't have humans, then you can may as well just do with machine learning, right? But then you don't have any creative thought, right? You need the creative thought. The visualization inspires to think about the problem and solve it, right? With like unknown solutions that you so far don't have, right? So you need a little bit of domain expertise to help you with that, right? And then you put things together and then create a solution. What else do you need? You have the humans, computer, algorithms, data. What else do you need? You need understanding of humans. You need to figure out how humans consume the visualizations, how humans react to those visualizations. Does it help humans at all to come up with these creative thoughts, or are these visualizations useless? So you need to understand how humans perceive. You need to understand how humans have cognition, and you need to understand how humans interact with the visualization, right? So for this, you gain this knowledge by experimentation. So you're gonna create some visualizations and let humans play with it, and then observe how they do, how they solve a problem, and how well they solve the problem, right? So in this class, we're gonna really talk about all of this, right? We're gonna talk about different kinds of data and how to clean it, talk about the algorithms that analyze the data, we'll talk about the algorithms and how they run and which ones are more efficient than others and how to store them and how to make them smaller if needed, talk about the humans themselves, how do they interact with data, what visualizations work better than others and why, and we talk about how to experiment with humans, how to figure out if a visualization is good or not, if it's actually the visualization you made is better than the visualization that has existed before. So we're going to talk about all of these things in this class. Okay, and all of this is basically called visual analytics. Visual analytics is the triad of data and algorithms, interaction, and visualization, right? So that all goes together. Analysis, interaction, and visualization. These things go together. That's why it's called interactive, human in the loop kind of process. Okay, so John Snow's, back to the cholera map, right, 1854, had all of these things. It had collected the data, it assimilated it, it did some statistics, very coarse, just clustered them around, but plotted them and clustered them. It visualized them on a map. It had the computational analysis, which in that case was only in the brain because there was no computer back then, so all of this was done in John Snow's brain. And there was domain knowledge. He was a doctor, he knew about the hypothesis initially, he knew about cholera, and he had some idea how it might get propagated, right? So domain knowledge all was there. And so this really is a really early case example of visual analytics. So now, this visualization again. So another example that I want to highlight here is more recent, 40 years ago, a little more than 40 years ago, about the Space Shuttle Challenger. You may not know this, 86, but back then this was the Space Shuttle launch. Space Shuttle program was very famous, started much earlier than that, and at this particular launch, they wanted to put the first human civilian into the space shuttle. Up here on the right hand side is Krista McAuliffe. She was actually a high school teacher on Long Island, up on the right hand side. And she was the first civilian. All the other guys are professional astronauts or scientists from NASA. And she was actually the only one who wasn't like a scientist, was just a civilian. So this was a very important flight because it was supposed to prove that space flight can be okay for regular humans. You don't have to be an astronaut for it. Every human can do this. Can stay in the space shuttle. Can do all the tasks. Can live and eat and read and breathe. You know, it was a very important flight to make for the space flight a little more, you know, like commercial. Right, the first step to commercial space flight. Okay, so it was a very important flight. So back then, when they launched, unfortunately, 73 seconds afterwards, this is what the camera saw. So this is like basically the space shuttle disintegrating in two separate pieces, right? That one flew this way and one flew this way, and you can just imagine humans died. The people on board died immediately, all the 7 ones of them. So it was like a disaster. Right, complete disaster, was investigated in Congress, and big issue, right? Very sad, and it really was a setback to commercial spaceflight, big setback commercial spaceflight. So now I explain you, you know, what happened. What happened, we know. What was the cause? You know, and this is really to go into the cause. Here's like a picture that was taken at the day of the launch, or like a few days before the launch. You know, this is the launch pad 39. It was 36 degrees Fahrenheit, just above freezing. Probably during the night it froze, and there's like water. There's like these icicles coming down. You know, I mean, this is something when if you have been in Florida, you never see that in Florida, right? Cape Kennedy is in Florida. You never see that. It's like a very unusual scenario, you know, and you know, so. Just to give you a little bit of insight what that might do to a rocket. So here's a space shuttle. There's a fuel tank in the middle. Then on left and right are the rockets that propel them up into outer space. And these rockets are made out of sectors, individual sectors. They're very big, right? Long rocket. They're made out of individual sectors. And these sectors are joined by these O-rings, right? So there's these sort of flange into one another, and these O-rings insulate them. You know, this is the sort of fuel is inside the rocket, right, and it can't go out because these O-rings seal it off, right? So this is where you basically what you need, right? So this is really much what it looked like. And you know, you can see from this the picture, like one of the camera pictures taken right before the explosion, you can see some fuel going off this rocket here, right? You can sort of see this. It's already lit up, right? Already ignited, and you can see it here. And this is just right after here. You can sort of see that fuel was able to go through the O-ring, go to the outside, and then, you know, in this high speed, it would then, you know, combust, right? And then this whole was like a whole chain reaction. Then the whole thing went up in flames, right? So that's what happens. Okay, 58 seconds after ignition. So, and then 73 seconds later, the whole thing went like a different place, in different pieces. So, what was the cause? Okay, we know what happened now. What was the cause? Could it have been prevented? Of course, that's the most important part, right? Could it have been prevented? So, so let's talk about this, right? So engineers at Tycol, who is the manufacturer of those rockets, they had a hunch before the launch. They said, well, wait a minute, you know, 36 degrees, you know, that's pretty low temperature, you know. I mean, we don't really know how this will behave. You know, we have never really, you know, tested that kind of, you know, a launch at a low temperature like this. You know, so they called NASA and said, you know, we have some thoughts and some concerns. Maybe you shouldn't launch this, okay? You know, and then NASA said, wait a minute, I mean, okay, but do you have anything like that makes you think that, you know, anything scientific that you can tell us about this? You know, you can just tell us not to launch. You know, we're on a schedule, and there's some other reasons which I'll tell you later why they really wanted to launch. Okay, so in any case, they asked this company to provide some background information on it, and so they sent in 13 charts to make their case. So chart number 1 was just temperature concern on SRM, that's a solid rocket motor joints. And then 27th January 1986 was the date at which this chart was made. Okay, this was slide number 1. They have concerns. Great. Number 2 was basically teaches about past damages to O-ring, this O-ring that joins the sectors together. So, so there was some information about it, like different rockets, 22A, 23A, and 22A, and and some like erosion depth that they measured, and perimeter affected of the erosion depth, the nominal, length of the maximum erosion. All these things they measured after, these are used rockets that have been used in the past. They measured this. And they made these measurements, and some of them they didn't actually use on a rocket, they just used in other studies. Okay, this was like a next slide. Number 2 and 3 was basically identifying a little bit more like what can happen to those O-rings when when things don't go well, like what the function is, that it sort of spreads apart. That was the next slide. And then some slide 4 and 5 that talked about the temperature together with the observations they made. So one of them, SRM-15, had 2 case joints, was 80 degree, much worse visually than SRM-22, which is here, which has blow-by. That was actually at the low temperature. So it turns out at high temperature, the visual was actually much worse than at a low temperature, right? And then there's some other guys too, and they list them here, okay? And that's what basically all the NASA people saw, right? So this is like really, so one of them at the high temperature had actually a worse observation at the low temperature. So now you're supposed to look at this and make a conclusion out of that as a NASA engineer, right? Or as a director of NASA. So I'm asking you, given this information, that's all I showed you, right? With these slides here that I showed you, would you vote for a launch? Or would you, basically ignore about what you know about the consequences? This is like very dangerous, right? It's a risk. But keenly be aware of this background here, which is very, very important. Because just a few days after the launch was going to be President Reagan's upcoming State of the Union speech. State of the Union in the US is basically where the president goes out once a year and talks about the nation and the state of the nation, right? Very important speech. The most important speech a year, right? So he was going to like brag that now NASA has successfully managed to put the first civilian in space, right, which opens the gate to commercial space flight. And, it's going to be like a really big profit, very pride of the nation, right, we can do this, and so, they're going to like probably have like some live footage of Christa McAuliffe in the space capsule, right, up there, high up in the, in space. Big public relation, gimmick, right? And this would help NASA a lot because then NASA becomes very relevant, right? NASA had funding problems before, but with this kind of PR, NASA would get a lot of attention, a lot of positive feedback, right? And they get probably a lot of more money and could implement all these kinds of dreams that they had, right? So now, given this, now you are the NASA director, right? And you have to make the decision. No, I will not launch because I don't know, what happens. The temperature is really low. Company has warned me that I shouldn't launch. I'm okay with a PR disaster. I'm okay with possible budget cuts. All fine. I'm going to put humans first. Or yes, rocket company is too cautious and really gave me some concerns. I really don't know really what these concerns really are, right? I mean, they could just be like, doesn't have to be, it's just some being overcautious, right? There's no real evidence. Remember, like there was one at high and low temperature, both of them were bad. Could just be some random incidences. Let's hope for the best, right? What happened after, we all know. They exploded, they launched it, they exploded, right? And of course, later on, always smarter. So presentation, let's look at these recommendations, why they failed. Okay, why the recommendation failed. Well, the presentation only had 2 shuttle flights. 2 shuttle flights. Everything else was not a shuttle flight. They were just, observations. One had a blow-by high temperature. One had 2 blow-bys at low temperature. And all the other shuttle flights completely ignored, right? And statistically very weak. One, you can't do any statistics on one, right? O-ring, recommendation was O-ring temperature must be greater than 53 Fahrenheit at launch. Okay, but there was only one sample size, one. There's no other, couldn't contextualize it, couldn't see any trends because nothing else was given, right? So you couldn't do any trend analysis or anything like this. No statistical average. So, lots of numbers and facts, okay? And this is really bad, right? Lots of numbers, information overload, no clear presentation, no good communication of the data, And this is what's supposed to be, you guys be learning in this class, right? But back then, there wasn't any. That's like there's no causal evidence that could predict this from this, right? Low temperature to crash. This is what you want. Low temperature to damage. This is the relationship you want to show with your data. You don't want to show blow-by erosion. You want to show damage. You want to show a graph like this. Something like this. Temperature, damage, and a clear trend. Right? That's what you want to show. Everyone who sees this graph or this plot can relate and come up with can make a decision really clearly. Right? Temperature low, damage high. Every idiot will understand that, right? So, but they didn't have that kind of graph, right? This is visualization. This is like in a split second, you can see what's going on and will not launch. Everyone around the table will vote no when you see that, right? Everyone will vote no. So how do you get to this? You need a measure for damage, right? You didn't have a measure for damage. You had a measure for erosion depth, the circumference of it, right? These are all sort of numbers, right? But they're not really, they're not showing you what the effect of it is, right? They don't show you that, right? So what Edward Tufte did, after the fact, of course, he made this kind of chart here, this kind of table here. First of all, he ordered the flights by temperature, okay, in reverse order, 53, 57, 58, 63. All of them, the flights before the launch, right? Order them in temperature, because the temperature is the one that's in the question. That is the dependent variable, right? That is what you want to order things by. And then he listed erosion incidents and said, okay, there were 3 for 53. And he looked a little bit at how severe they were, blow-by incidents, how severe they were. And based on that, created an index called the damage index. Right? Took all this, multiplied by severity, created damage index. Take that, multiply with severity, damage index, right? And then get this list here, and then plot it like this. Just plot it like this. Just take a simple chart, temperature, damage index, and just plot them and label that. You can already see a trend, but for those who don't see the trend, you can make a nice fitted regression curve, polynomial regression curve, and visualize it with this low-tech graph, right? Very low-tech. And everyone will see at 36 degrees or 32 degrees, this is catastrophic. The damage is catastrophic, right? Every preschooler will see that this is not good, right? And no one will launch. This is like a storytelling with a simple visualization and a labeled graph, right? That's all you need, okay? So the key is put the numbers into a picture and visualize the right metric, okay? 2 key issues, right? 2 key things. So this is what the congressional hearings, what people saw. This was before this came out, right? This was like after the fact, much after the fact. This was basically a textbook example how to present data. And this is really a textbook example how not to present data, right? What they did in the congressional hearings, NASA, they would take these rockets, make them cute looking, like each of these little tiny rockets, make them cute, make them look like rockets, order them by SMR number, not by temperature, by SMR number, which is ridiculous because you want to order by the dependent variable. And then, plot the temperature on top of it and make a little bit of icons like what the damage was, right? That's it, right? So there wasn't anything there, right? So, there wasn't anything there. So this was hard to really see what is going on here, okay? Assimilate information. Then at the congressional hearing, what they said was, the congressman said, oh, okay, this looks really random to me. I think NASA couldn't predict anything. And I think it was just a case of bad luck, and let's learn from it and not launch at low temperatures. But you couldn't know that beforehand, right? It's so complicated, right? There's so many factors. Basically confuse the audience by unclear visualizations, right? If they had seen this, they would have pointed their fingers at NASA. Had they seen this, okay, So it's a very interesting, right? Confusion. Okay, beautiful visualization, very graphical, but not presented anything in any way that you could make conclusions from it, right? So this is basically how you can lie with visualization or confuse with visualization, right? So it's a good example and a bad example. So you can read more about this from these books. You know, there's these books by Edward Tufte. You know, they in the library. I read most of them. I think I read all of them over the years. You know, they were actually very early books, 83. We'll talk a little bit about. We talk a little bit about these things later on. And you know, Edward Tufte actually is a really famous person in visualization. He taught information design at Princeton University, and now he's a professor at Yale. He gives talks. You know, you have to pay like $2,000 or something to go to these talks. He's a visionary, has really pioneered visualization and had some really good ideas, and which I will talk about. You know, very good ideas, and you know, very basic. But there's also things. He's a very fundamental kind of person. So we'll talk about this in later lecture. So he's a pioneer. If you can catch him, he's a good to see his talk. So course topics. So we'll talk about non-spatial data and spatial data. You know, and then data mining. Talk about data analysis topics. Talk about humans, how they see data and how they have cognition processes. Talk about large and big data, all with the purpose of showing you how to visualize, interact, analyze the data, that the human observer can get insight and knowledge from that, right? So this basically in one slide. Okay, this is CSE 564, but the same thing. Okay, so give you some example to spatial data, right? So now spatial data is basically data that have a spatial reference. So every data point has a XY or XYZ or XYZT temporal component. Every data point has it. So you can sort of map them nicely to space. For example, you can have a shock wave, some data about shock waves, how shock waves propagate over time. Basically, the shock waves were computed in a supercomputer, and then the scientists need to figure out, based on this data, basically need to see how the shock wave really looks like, and how the shock wave interacts with particles in space, and how it propagates in space, right? So you can create a visualization based on that, right? So this really are one of the first customers of visualization, because before these simulations, you only had data points, numbers, but you know, no one really how to understand these numbers if you don't visualize them, right? So here's a visualization of that, right? You know, so you can visualize them. Spiral flow is another one. You have a simulation of spiral flow, and then you visualize those data with with volume rendering like this, right? You give it some colors that distinguish different things. You know, put like yellow, put them on a color map so you can sort of see the fast areas in red and the slow areas in blue. You know, so this helps you figuring out like the dynamics of things. Then here, transparent MRI head. You can scan a person's head and then you can see how the brain looks in relation to the skull. You know, virtual frog. You can scan a frog and then dissect the frog in a virtual space. You know, like you can use volume rendering to see how the bones look like in the context of other organs, right? You can also remove some organs virtually, so you don't have to kill any frogs. You can just dissect it in a computer, right? Nerve cell here is like you obtain some data on a confocal microscope, electron microscope, and then visualize it with volume rendering, so you can sort of see what a nerve cell looks like on a microscopic scale, right? You couldn't see that any other way, right? You can really now have a three-dimensional rendering. There's like a graphics here that creates this picture, the shading, so you can see 3D and you can sort of see, how spatial elements relate. This is basically a process called volume rendering, and you can give it any color, right? In this case, you give it green. Nerve cells don't necessarily are green, but you can make it green. Here's a semi-transparent tomato, also scanned wind flow around the globe, and here MRI head. All of these things are basically spatial visualizations rendered by volume rendering. So let's look at some spatial data in particular. Okay, so all of these data sets are usually obtained by 3D volumetric scans. Like for example this mouse, right? If you want to see what a mouse looks like inside, before there were scans, you had to actually cut it open. The mouse didn't really like that too much and actually died afterwards, right? Now you can keep the mouse alive. All you have to put the mouse inside the scanner and then volume render what you got from the scanner, right? So here's like a volume rendering. Basically here the skin was already removed by the renderer. You can sort of see how the bones relate to the organs. You can sort of see how many joints it has and how flexible the mouse actually is. You count the vertebrae, and you can see the shape of the skull, things like this. You can rotate around all interactively. The volume renderers nowadays are very powerful. Then you can change the ISO value. You can expose, you can sort of figure out, you can basically, look at the skin instead and then bring back the interior. And just like, interactively, you can change those visual parameters. You can really figure out what the mouse looks like, and you can teach veterinary students or something like this, or others, like what mice look inside, right? Then another thing is spatial data is like data sets obtained by 3D simulations that I told you already. There's some examples is like, how do planets form by ways of gravitational instabilities? That may be an interesting thing. And you may make a simulation, and you have a hypothesis that matter clumps together and attracts more matter as we go, right? I mean, we know this. This is like how the universe was created, right? Matter clumps together, attracts more matter. And you make a simulation, try to show that, right? And then the simulation, just a bunch of numbers, and you want to visualize it so people understand how it really happens. And here's such a video, from such a simulation. This is a volume rendering again. And over time, as the simulation goes on, you can really see how this red, sort of these matters outside, really start clumping together in the center and create this sort of, hardcore, more massive core, right? You can really see this over time, right? It looks good, right? It has like semi-transparent material where you can see through to the core, right? Based on qualities that you define, right? So it's like really, makes a picture that is understandable to everybody, right? You can put that in museum. Scientists really need it to prove a point. So, this is more of a post hoc analysis, a post hoc visualization, where you try to look at the results of an experiment. It's not visual analytics in that case, where you try to steer a visualization, where you steer a computational process. Here it's more of a post hoc thing, right? So we'll see that you also have visual analytics where you steer the computational process, and we'll see this in another slide. Okay, and non-spatial data essentially is data where you don't have a spatial reference. Here, there's no X, Y, Z or time. It's just data points that describe an item, right? In this case, a car, an object, right? Miles per gallon, top speed, acceleration, number of cylinders, horsepower, weight, country, origin, and so on. These are all parameters that describe a car. And there may be clusters of cars that are similar. There may be some features that favor other features. So you want to sort of know how these things relate to one another. So you can select a car. You can see the trade-offs. Like maybe acceleration has something to do with weight, and maybe something to do with miles per gallon. So there's trade-offs. Recognizing them, requires like multivariate analysis. Okay, here are some pictures of cars. They don't really help you much in that kind of task, but that you can decide on like if you like it, the look of it. This is like a spreadsheet that you would have. This is not a car, but this is the kind of spreadsheet. Columns would be different features, and the rows would be different cars. There's nothing you can really see here. You can just see the numbers. A better visualization really is this. So this is just one example of a multivariate visualization that you may not be aware of, but which is everyone I show this, scientists, doctors, and business people, they did not know this, but when I show them this visualization, they all like it, without exception. It's like a well-hidden secret, right? It's only known really in the scientific world and the visualizations, but really when you go out into the real world, most people don't know parallel coordinates. So let's talk about parallel coordinates, what it is. So basically parallel coordinates, each of these vertical axes is basically an attribute. Mile per gallon, this one cylinders, this one is horsepower, this one is weight, this one is acceleration. Actually, this is the time it takes to go to 60 miles an hour. This is actually the higher the number, the slower the car. Year and origin. And each of these lines, each of these thin lines is basically a car. So up here is a car that has really high mile per gallon. But this car here, when you go down the cylinders, has really no number of cylinders and has really low horsepower and low weight and takes a lot of time to reach 60 miles an hour. And then this car here has a really low gas mileage, doesn't give you a lot of miles per gallon. Those has a lot of cylinders, has a lot of horsepower, a lot of weight, and really takes a very little time to go to 60 miles an hour. Then the year and the origin are really, there's no real true correlation here. So what you learn from these are like, these fat lines are essentially sort of midlines of means of certain clusters. That is the red cluster, the green cluster, and the local blue cluster. These are the red clusters are the very powerful cars. The blue clusters are very, very efficient cars, and the green ones are sort of in the middle. Okay. So what you can learn from this, really, just looking at it, you can learn that horsepower has something to do with weight, or better weight has something to do with horsepower, right? When you have high horsepower, you gotta have high weight. You gotta have a heavier car. But horsepower, if you have high horsepower, you're gonna get low time it takes to go to 60 miles an hour. But unfortunately, low horsepower needs a lot of cylinders, and that takes a lot of gas, right? So you can learn a lot about cars by looking at these relationships in this combined plot, right? If you only looked at two-dimensional plots, scatter plots, or pie chart, or anything like this, you never see this, right? But here, with this high-dimensional multivariate visualization, you can easily see it. So this is just one example of a visualization and there's some interaction that makes the red, the blue, and the green cluster. That helps you a little bit easier to see what's going on. We talk about this. So, this is just one example of these multivariate ways to see things that we're going to learn about in class. Okay. Then big data, lots of big data. So, everyone knows this, and this is what we're going to deal with. And basically, one time a student came up who was a scientist in atmospheric science, told me about the scientific method, and if the scientific method applies to data science as well. So I thought about a scientific method, which is here, right? You probably all know the scientific method from your earlier education. If you don't know it, I'll tell you now. So basically, the scientific method is always like this. You formulate a question, you generate hypothesis, then you design an experiment that can help you verify or reject the hypothesis. You form a testable prediction, like something that you can help you to verify or reject the hypothesis. Collect data that help you to do that, right? Analyze the data, test the prediction, and publish the results. It's easier publishable if you actually can accept the hypothesis or verify it, and harder if it doesn't work out, right? But that's what science is, right? So this goes on like this. If it doesn't come out well, maybe you have to change the hypothesis and make another experiment and test it, right? So it's basically an endless loop, right? You keep doing this, right? But for this is sort of the general experimental, scientific method as scientists use it. So now, how does it work in data science, right? In data science, you experiment, you don't have to form it. You don't have to actually take people and conduct experiments on them or crash cars or do something, right? You can just find data on the web that will tell you about, that give you insight. That is the experiment already in there, right? So the data may not fit it perfectly. Maybe you have to, segment a little bit. Maybe you have to find several data sources that sort of combined create the experiment. Remember John Snow? He conducted an experiment based on the cholera death data and where the cholera deaths occurred, right? So this is an experiment, right? There may be some outliers, there may be some noise, there may be some conditions that are a little bit adversarial, right? There may be some confounding variables. Have to find all these things out, right? Maybe missing data that are there. All of these things happen, right? But in event, you can conduct an experiment just by finding data sources. And then once you have the data sources, you form a testable prediction, and then you scrape and mine the data, right? You collect the data, you scrape and mine it, as I said before, right? Basically, that's where you find the data that you really want. And then you analyze it and visualize it, right? This is like how you tested the prediction. You visualize the result and then publish it or do more experiments or find more data, right? So basically, same thing, right? find that the other thing is just you, instead of forming an experiment and subjecting, creating the actual experiment, and then, you find the data and you mine the data. You don't collect it, you mine it, and then you visualize it, right? So this is basically age of data science. So the same process applies. It's just now you have more tools on your hands. You can just go to the web and find data or collect them, right? So this is basically that. So visual analytics versus data science. So maybe you all have taken the data science course that this Stony Brook has. Maybe you have not taken it. In a sense, visual analytics is basically in the center here, and all the data science things are around it, right? So your knowledge discovery, statistical analysis, scientific analysis, geospatial, and some other things come in play too, cognitive and perceptual science, interaction, presentation. All of this is basically visual analytics. This is the data science view, math, statistics, advanced computing, visualization, all of these are peripheral, but data science is in the center. So no matter where you look at, it's always the same thing, right? It's one thing is the data science aspect, where the data gets analyzed, and the other side is more like where the human is in a loop and can participate in the data analysis process. I have to tell you, I like this one here better because I call that visual data science, right? So this is basically visual data science. I try to engage the human in the data analysis. So when you look at the data scientist, okay, try to be, this like it can be a female or a male, right? So when you look at the data scientist, what the properties they have, right? I found this, I really like this picture because it really sums it up nicely. First thing they have is math and statistics background, right? You would know something about machine learning. You may not be an expert in it, but you know something. You would know something about statistics. May not be a statistician, but you know something about it. You know something experimental design, supervised learning, unsupervised learning, optimization. So all of these things we're going to talk about in this class, right? To really give you some tools that help you, analyze the data that you're going to visualize, right? So we're not going to go in great depth about it, but I show you some techniques that you can use, right? Second one is programming, okay? You're all computer scientists, right? So you all know programming, you all know Python, you will all know JavaScript hopefully, or maybe learn it, it's not that hard. You will all know JD3. And you're basically going to take this stuff here and program it and turn it into an application that humans can use, okay? Then you will have domain knowledge. So this is basically where you as a visualization expert try to find friends in the domain, right? You're going to partner up with a scientist who can look at your visualization and give you some input, like what to look at and how to look at it and what works and what doesn't work, it helps if you yourself are passionate about data, if you're a data scientist, you must like data. You must be easily, affectionate. You have to be affectionate about the data that you are going to analyze, right? Maybe you don't know everything about it, but you should try to learn about it so you can have a good communication with the scientist or your customer. As a visualization expert, you're never alone, right? You always have a person who needs what you produce, right? So you're gonna have to have some friends, and you're gonna work as a team, right? So that's really what you are, right? And then this is really the part that is really your place, communication visualization. That is where you really apply your knowledge, right? You're gonna produce something that the human can use, right? And that engages the human, helps your domain specialist get the insight, right, that he wants, and is interactive and engaging and gets addictive, right? People want to always play with it, right? That's what you want, right? So and I teach you about this too, right? I tell you how to tell a story with data, tell you what makes a good visualization, what doesn't, tell you which visualization work with what data, stuff like this, right? And then you're going to program this for your projects, right? So when you look at this, when you take a data science course, then you always have this data-driven decision making. Everything is automated, data engineering, right? So everything is automated. It's just the human is in the end just say yes or no, right? There is no real human involved. So what I'm adding here is the visual component, right? I get the human in charge, help the machine to come up with the decisions, right? And debug it, right? You don't want to have you want to instill some trust in what you're deciding on, right? If you just blindly believe the machine, then you may run make the wrong decisions, right? This is what's called explainable AI, right? Which is a hot topic, right? Otherwise robots will run your life, right? You want to be in charge, and you want to be examining the robot's decision, and maybe program the robot better based on that, right? You want to be the one. You're going to be the one in charge, and not the robot, right? You want to trust the robot and always second guess it, always, right? And visualization is the perfect way to do that. Okay, so I call that visual data science or visual data driven decision making. So visualization, okay, all of foremost, visualization should be fun, okay, should be beautiful, and it can be nowadays with D3 and Plotly and Tableau, all of them are very beautiful, good-looking visualizations, right? This is like a stream graph. This is a force-directed layout. This is a word cloud, parallel coordinates, bubble chart, tree map, radial tree, right? All of these are really easy to look at, right? They're really nice, and once you play with them, they look even nicer because they're all interactive and reconfigurable, right? It's fun to work with them, right? And that's what you want. You want to make something fun and responsive, and responsive is the key, right? No one should wait for something, right? Users want to see instant results, so that's basically what these things will do, because visualization is fast. When you look at this picture here, quickly you saw that there's a red dot, right? I mean, you could not help it, right? You saw that instantly. You saw that there was a red dot, right? And that's actually less than 200 milliseconds to recognize this, which is called pre-attentive visualization, right? You actually saw it before you could actually pay attention. It forced you to look at it, right? No matter, this was like basically it's an evolutionary skill, right? You're gonna draws your attention without you even wanting it, right? You can't prevent it, right? So this is really an amazing advantage of visualization because the brain can do this very fast, right? It can detect changes in orientation, it can detect changes in size, changes in shading, in color, or it can changes in shape, proximity, like shape again, and here the orientation again, some other graphical detail. Brain is very fast in that, extremely fast. You see this quickly, right? So that's because your brain is massively parallel in recognizing these sort of visual attributes, right? There's like one part in the brain that can do color really fast, one part in the brain that can shape really fast, one part in the brain that could do motion very fast, right? And then one part of the brain that can do this very fast, right? So there's different sections of the brain that are responsible for different parameters of visualization. So this helps you to really quickly recognize there's an insect in front of you, what color it has, what type of insect it has, and then having this all together in a single representation then allows the brain to look up what you know about insects and things that fly around, right? It will tell you maybe you should stay away from it because it may sting you, or maybe that insect doesn't sting you because it doesn't have, doesn't look like a bee or a wasp, right? So it basically it triggers information that you already have in the brain and helps you to draw conclusions based on that, right? So it basically triggers lookup of information that you already have in the brain, and then you can reason with it and create actions or change something. This is really what visualization does, right? It basically stimulates thought, right? And this is because more than 50% of the brain are dedicated to visualization, right? So visual information, basically, there's a lot, like a storage of it, the circuits that reason with it, the circuits that recognize, and the circuits that detect it, right, and do edge detection, all of this. Visualization is a very early skill, because for humans to have become humans, you needed to know what your environment looked like. Otherwise, the environment would eat you, or otherwise you couldn't eat the environment, right? The eyes were very important, and they got developed very early on over 10,000s of years, or 100,000 of years, right? So that's why it is good, right? So give you some demos. So you have to be interactive. So here's like a demo of a force-directed graph. So it's interactive, right? You can run it again, You can pull it around, right? You can take data and then you can see it react, right? So basically this graph here encodes associations of data items. So these data items are all associated. This is the main head of the cluster. These are also associated, and you can change it. You can change this, pull this out. You can see like different associations. You know, you can pull another node into the center. You know, so you can make that the center, right, and node things around. You know, it's responsive, right? You can create a new visualization based on that. So that's what that is, and this is all in this website, Data-Driven Documents, D3. You can see a lot more of these. So visualization has a long history. You know, everyone knows cave paintings. Very early humans did this. So people already liked drawing things, you know, and trying to show different aspects of things. You know, here they got drawings. Visualization can be inspired by art. So I have a few colleagues, actually they have a book on art next on their desk, right? For example, some colleagues have medical illustrator books on their desks because they want to create better visualization of medical aspects, right? So here, want to show the hand, and you want to show, this is like a drawing, and this is the computer rendered equivalent of it. This is like humans drew this to show students how a hand works, right? What are the nerve fibers, what are the blood vessels and so on, right? And then nowadays you can create this interactively on a computer with volume rendering, right? The same thing. You can basically be your own artist, right? Here, this shows you how a fish, what's inside the fish, you know, cut away things, you know, and then these are like, you know, motion blur, where you can sort of see like the motion of this engine part. Here you can see focus and context. You can see some things are in focus and other things are not, right? Okay, so this is basically that part, and here you have focus and context, where you can sort of see the focus region of these vessels, and everything else is a little bit, this is very drawn at very high detail, and everything else around it is a little drawn at lower detail. So it tries to focus the viewer on this particular part of the picture, but give context on the surround, right? This, like, artists have used this for a long time, but now you can use this on a computer too, right? And this applies to many domains, not just the heart, right, or lung. It applies to information visualization as well, right? So this is a very, very interesting, very good, very useful concept. Visualization can be deceptive, of course. You know, so this basically, all these deceptive visualizations basically abuse the certain, you know, properties of the human eye and the human mind, right? The human eye usually only looks the way it works, the human cognition works. You look at small neighborhoods, and your eye moves very rapidly around a picture to understand what the overall concept is. So when you look at this neighborhood here on the left, it looks perfectly fine. When you look neighborhood of the top right, looks perfectly fine. Bottom right looks perfectly fine. But once you look around and sort of try to integrate it in your brain, you'll see, well, this doesn't make any sense, right? This is like an infinite loop, right? This is not, you cannot manufacture this at all, right? But, you know, so this is deceptive, right? Because it plays a joke on your visual system, the way you work, right? You look local detail and then you integrate in your brain, and then this does, and that makes you look, that makes basically deceives you. Another one is this one here. Looks perfectly fine in a local neighborhood here, right? There's some people standing here on a ladder, but then when you look up, actually this folds over, right? This is actually the top now, right? And this is on the bottom, right? So this doesn't make any sense. Looks perfectly consistent in a local space, but doesn't make any sense once you integrate it across. Again, another example for visual system where you can fool it, right? By knowing this. That the eye, you can never really understand. It's very hard to understand, right? You just know it's wrong, and it makes you laugh because you're embarrassed because it's wrong, right? Another thing is this one here. Count the black dots. Can never count them because whenever you look at it, it disappears. This is another property of the visual system that is because local perception is different than peripheral perception, right? And that plays a joke on you. Once you look locally, it looks very different than peripherally. And that I have a lecture on this and I explained that to you. But this is basically another reason why visualization is not optimal. Right? There's always things you can find, that makes it less appealing. Here's another one. There's nothing moving here, but it's only because whenever you look somewhere, when it's moving, you automatically look there, and then it's not moving anymore because things in periphery look different, are perceived different than things in the center, right? In the focal region. So that's why this moves, right? If you keep your eye always at the same place, it will stop moving. It's actually very interesting, right? But then it starts fading away because you need those saccades to understand the scene. Otherwise, okay. So this is another one, visualization deceptive. All these lines are straight lines, but they're actually not. They're straight lines, but the people think they're not because of this very interesting way you offset these black squares, right? Trust me, but it fools the visual system, but they're all straight lines. Another one is this one here. The elephant has different feet depending where you look at it, right? And that's basically because you only look at a local region but not the whole. Right? This one is also interesting. This is more about the perspective vision. This basically creates an illusion of perspective vision, right? So basically here, this woman looks like she really lies in this pool, and the leg is sticking up. But really, when you look at it from another vantage point, then actually this is not the case, right? Actually, this is just drawn in such a way that when you stand there, this long foot makes you think this is upright, because I have a little visualization that shows how the eye looks at it, but eventually this is perspective foreshortening, right? This is what it would look to you, if you looked at it a real foot, right? You just fool that system, right? You can make geometrical arguments that how a two-dimensional picture is mapped into the eye when you look at it, make the same impression than if you looked at a three-dimensional picture directly, right? So you can actually show that, right? Then another one is this one here. This is more important for the information visualization, right? Depends on the contextual environment. The size is dependent on the contextual environment, right? So the middle circle here is exactly the same size than on the right-hand side, but it looks much smaller because everything around it is much bigger, and it looks much bigger here because everything around is much smaller. So this is a very common trick to make things bigger than they really are, or to make things smaller than they really are, right? So it's because the visual system integrates the scene around it and creates some sort of relative impression. It doesn't look at the absolute size; it looks more at the relative size, and that's what conclusions you derive from that. Another one is here. This is really serious deception, because it basically abuses on the way you look at graphs, right? So this has actually really appeared in a publication by the Florida Department of Law Enforcement. You look at it, the number of murders committed using firearms, gun deaths in Florida. So this makes you believe, right, that in 2005 they enacted the law, Stand Your Ground, and it makes you believe as if the number of murders went down. You think, wow, this is great. That this law really did something. This law has really decreased the murders. But when you really look closely, this plot is actually folded upside down, right? The higher numbers are on the bottom and not on the top. Usually, higher numbers are always on the top. Higher numbers are never on the bottom, right? You usually have always the base axis on the bottom, and then the y-axis goes upward, but here the y-axis goes downward, right? So in effect, the number of murders went up and not down. Of course, this is really bad, right? This is really deceptive. But this really appeared. This is amazing, right? That this was allowed to appear in a government publication, right? Just to make a point. It's fake news, right? So next one is basically power of the visual system. Okay, it's not perfect, but extremely powerful. It's not perfect. So it's not perfect. So you have to know what the limitations are. But once you did play it the right way, it can help you a lot. Right? It's an integral part of life. Everyone already knows vision, so you don't have to teach anybody. It's a gateway to higher level regions of the brain, because you look at something and then you can trigger things you have learned in the past, or you can trigger creative process to like think about things, you know, because oftentimes there's a visual thinkers and audio thinkers. I'm a visual thinker. Like when I look at something, I can see it much easier what's going on than when I just hear about it, right? So vision is a really good way to reason with things and to learn to make conclusions and to derive new things and get insight. So basically what you want to do, you want to exploit this fast and powerful processor for complex data analysis, creative tasks, and communicate ideas, right? And this class will tell you how to do that, right? It will basically tell you how to use visualization for data analysis. Could be very complex data and get insight from them and help other people get these insights too. People that are not experts in visualizations, like give it really to the common people, the mainstream people, to really make visualization a part of their analytic process, right? That's what I try to teach in this class, right? So this is called the science of visualization, visual analytics. So textbooks. So what I really want you to, you know, I'm not saying you have to buy them, but, you know, definitely be aware of them. This book here I recently added, just the first time I have this, called Interactive Data Visualization, the second edition by 3 researchers that I know and value very much. It really, every chapter really talks about something that we talk about in class. It is a really great book. Data mining is a book that you may want to have to learn about data mining, and then how, you know, really good book about data mining. Really tells you a lot about how to process, how to make sense out of data, right? How to process it. Clustering and lots of things are in there. Very, very useful book about data science. I thought it was the best book I could find. And then some other books that are there. Visual Thinking for Design by Colin Ware is a really good book about more human perception and cognition. I actually read this book and I really like it a lot. The new edition is just coming out and I'm actually reviewing that. And, you know, it's a really good book. I mean, if you want to learn more about humans, how humans think about data and how they perceive, it's a great book to have, okay, and to at least read or borrow. Another book here is Visual Computing for Medicine. This is more about the volume rendering. It's for medicine, but it's really applicable for lots of things. And, you know, you may want to also look into this when we talk about volume rendering. Now you see it is more of a casual book, but also very good by Stephen Few. Also a pretty good book. This used to be a textbook that I used in the early days. It's a really nice book because it really brings things home from a very practical standpoint, right? It's very nice read and it tells you a lot about interaction, how it works with humans and so on. So it's also a great book. Visualization, Analytics and Design is by Tamara Manzner. She's a very famous person in the visualization community and talks, it's more from a visualization, information visualization perspective, representation, you know, not so much visual analytics, more about visualization, hardcore visualization. And it's a good book to read about representations. You know, some things are shared among the other book, but some things are different. So you may want to look into this too. So tentative schedule. So every time I'll present this kind of schedule, I may change a little bit, you know, but I want to show you the projects. Third lecture next week, I'll have the first project out, you know, to just get the first project to get your hands dirty on implementing these kind of things. Then there's project 2, project 3, final project proposal, and so on. And then I'll have 2 midterms and then a final project presentation. There's no final exam, final project presentation. So what you can see, there's like 3 projects, each of them is 10%. Okay, then 1 midterm, 2 midterms, 20% each, and the final project will be a proposal, preliminary report, final report and presentation. That counts the most, okay? And extra credits will be given for projects, but you can't carry it over to other things, right? It stays within the projects, okay? And participation is not graded, but I hope you will attend regularly and participate actively, right? Ask questions. You know, I know 7 o'clock is a little bit late in the day. You know, in winter it's sometimes hard to get to the class, you know. But I hope you will come. Because, you know, oftentimes I say things that may not appear in the slides directly like this. Slide is usually only a little bit of a guide, what I will say, but I may say things to explain it better. You know, you can also ask questions if you have any questions. May say something about the projects. I'll make definitely use of Blackboard, so to communicate with all of you, so you can ask questions on Blackboard, and TAs or I will answer them. You can also answer each other's questions. Like, we really want to make this like interactive, right? So you're not going to be left alone for your projects, right? I really want you to accomplish these projects, okay? Late submission policy. Basically, the core message is be on time, deliver the stuff on time, okay? I don't want to give a lot of time after, because otherwise we fall behind with the whole schedule and then you don't get to do all the things I want you to do, right? So basically the clock starts ticking after the due date, okay? 10%, I think, something like this every day, right? So you really have to really make it a habit to deliver the stuff on time, okay? Then basically this is pretty much it. So if you have any questions, you know, then you can send me email. Other than that, hopefully it was very clear. I post the slides on the website, CSE 564. You can get all the slides from there. I have the video I already have, right? So okay. So thanks a lot, and see you later.